Hello, my name is Paweł Paris and I work at the University of Warsaw. I will present a paper called Higher Order Non-Emptiness Step by Step. What is this paper about? There are three parts of the title. Higher order, because we consider higher order recursion schemes. Non-emptiness, because we solve the language non-emptiness problem for these higher order recursion schemes, or equivalently, we solve the problem whether a given alternating reachability automaton accepts a tree generated by such a recursion scheme. Step by step, because our algorithm works in multiple simple steps. In each step, we simplify the recursion scheme. Okay, what are these recursion schemes? This is a generalization of context-free grammars in which non-terminals can take arguments. The arguments themselves can also take arguments. Moreover, we use this formalism to generate trees instead of words. Okay? It can be also said that this is a lambda calculus in which we consider the simply typed fragments and we add the operator of recursion. Another way of saying this is that we consider programs with recursion, with higher order recursion, where functions can take other functions as parameters, and where everything is well typed. Everything has some type, every function and every parameter. There are no data values, yes, no integers and things like this. Only recursive functions. Okay, so these are recursion schemes. Let me give an example. In this recursion scheme here, we have three letters, A, B, C. To each letter, we have to assign a rank, which is a number of children. So, for example, A has rank 2, which means that every node with label A has 2 children. There are non-terminals, S, A, and D. S is a starting non-terminal. There are rules like that. Here on the left, we have a non-terminal with parameters. So, for example, non-terminal A, it takes a parameter f. This parameter can be used on the right side of the rule. How does this recursion scheme work? We start with the starting non-terminal S. It's reduced to AB. This AB, it is an application, yes? All things here should be read as terms. So this AB means application of B to the function f. We read the rule for A, and for the parameter f we substitute b. Yes? Now this thing here starts with letter A, which means that we create a node with label A. The first argument is something that describes the left child. The BC describes the right child. The BC is just this tree with B and with child C. On the left, we again have something that starts with a non-terminal, so we reduce again. Now, instead of f in the rule, we substitute db, the parameter from here, and we continue. Again, we have something with a in the front, so it's this tree. Now, the right child is dbc, can be reduced using the rule for d to bbc. Yeah, b is substituted for f, c is substituted for x. So this is this tree. On the left, we again reduce using the rule for a. We get this branch and we continue like that. We obtain an infinite tree. We see that each consecutive branch has twice as much letters b as the previous one. So in particular, this tree is not a regular tree. Okay, such trees can be generated by recursion schemes. We have many examples of trees that can be generated. In the definition of recursion scheme, one thing is important, that everything has some type. So, what are the types? O is the ground type, a type of a tree. This is a type of a function that takes trees and produces trees. The next type is a type of a function that takes a tree and takes a function from trees to trees and generates trees, and so on. Such types can be assigned to everything here in this example. Okay, what is now an order of a type? This is one more definition, the last one. Order of the ground type of the tree, so of the tree is 0. Order of a function is 1 plus order of the arguments, maximum of orders of the arguments. So trees are of order 0. Functions from trees to trees are of order 1, even if we take more trees. Now here we take a function of order 1 as an argument, so this type is of order 2. Order of a recursion scheme is just the maximal order of types used in its definition, so maximal order of types of the non-terminals. Okay, this is the end of definitions. Now, what we want to do? So the general goal in this kind of research is that we want to verify properties algorithmically, verify properties of trees generated by recursion schemes. So why we do that? Recursion schemes are models of programs using higher order recursion. Yeah, so we have some programs and we want to check some properties of them. For programs in general, it's undecidable, but we can model such a program using a recursion scheme, and then some problems become decidable. We can solve them. The basic problem is shown here. We are given a recursion scheme G that generates some infinite tree, and we are given an automaton that reads such a tree and says yes or no, yeah, either accepts this tree or not, and we want to answer whether the tree will be accepted by G. This problem is decidable. It was shown by Luc Ong. It's decidable. For example, the automata can be chosen in many ways. Let's say that we consider alternating automata with parity acceptance condition. So these are exactly automata defining regular languages. Equivalently, you can take the MSO logic. This is very basic theorem here, which has several proofs. The original proof uses game semantics. It's also possible to use collapsible pushdown automata, which is an equivalent model, a model equivalent to recursion schemes. Other proofs use intersection types or Krivin machines. There are also some extensions of this theorem. There are also some papers that work only with automata with reachability accepting condition. So reachability is less than general automata with parity condition. And in this paper, I show a new algorithm that does the same, so solves this problem only for automata with reachability condition. This algorithm is quite simple. Okay, what is the complexity of this problem? It is n-fold exponential time. It's complete for this class. For recursion schemes of order n. Yeah, so we usually assume that the order of considered recursion schemes is fixed. It's at most n, and then the problem is n-fold exponential time, so quite high. But it's not so bad. It is linear in the size of the grammar, assuming that we have fixed the size of the automaton and the number of arguments, yeah, the arity of types in the grammar. Yes, so it's and the n-fold to the exponent to this n-fold exponential time, we only take the maximal number of arguments of the types that are used and the size of the automaton. But the size of the grammar, meaning the number of rules, number of non-terminals, it's taken only linearly. These results are valid both for parity automata and for reachability automata. Yeah, so the hardness, in particular hardness for this n-fold exponential time is already for reachability accepting condition. Our algorithm achieves the same complexity. let me mention that some of the algorithms, namely those using intersection types, they perform relatively well in practice. They can solve some examples, yes, in reasonable time. So they are just slow in the worst case, but on many examples they are relatively fast. This is not true for my algorithm, but for most other algorithms, my algorithm is always slow, always achieves the same complexity of n for exponential time. Okay, before starting, how the algorithm works. Before starting, we do a preprocessing. So we consider a product of the recursion scheme and of the automaton. I don't want to concentrate on that, but let me just say what is the result of such a product. This is a recursion scheme that generates a tree, which is essentially a tree of all runs of this automaton on the original tree. And in this tree we have two kind of nodes. We have OR nodes and AND nodes. And we also have two kinds of leaves, which are bottom and top. It's like empty OR and empty AND. And we ask about alternating reachability, which is shown on this example. Yeah, we want to find such a subtree, such a skeleton, that witnesses that this tree should be accepted. So here in this OR node, we just should go to one child. In the AND node, we have to go to both children. And here we have OR, so we go left, and here is top, which is accepting. Here we go left. Here we cannot go right, because here is AND, and below this AND we have bottom. So this subtree here is rejecting, but we can go to the left, and here we have again OR, we can go to the right, and we can accept. Okay, so this green subtree witnesses that the whole tree should be accepted. And now, having this preprocessing, we just have to solve this reachability problem. The general construction of my algorithm is that we have some transformation that takes a recursion scheme of order n and generates a recursion scheme of order n-1. We repeat this transformation many times until we reach a recursion scheme of order 0. At every step, the size of the grammar grows exponentially. At the end, we get a grammar that is n-fold exponential size of n-fold exponential size in the size of the original grammar. And for grammars of order 0, we can solve the problem in a trivial way. Okay, so the whole algorithm is of n-fold exponential time. We only need this transformation. Yes, we need the transformation that takes a scheme of order n, generates a scheme of order n-1, so that it generates a similar tree, a tree in which the reachability problem has the same answer. And how we do that? So the way how we transform the trees is shown here. Okay, we have a tree on the left. We have here a tree generated by a term KL, where L is of order 0. So it generates a tree. K takes this tree and it can only attach it somewhere. So K is kind of a context to which the tree generated by L is attached. And how such a tree can be accepted? So there are two ways. The red way here on the left is that already in this part generated by K, we can find this witness for acceptance without looking at all inside L. The other possibility is that we look inside L, and then both this part generated by K has to be accepting and this tree generated by L. And such a tree can be transformed into tree shown here, for which the acceptance is equivalent. Yeah? So this tree is accepting, even only if the previous one was accepting. So what is going on here? So here we have somehow two subtrees corresponding to these two cases. On the left we have this red case, that is acceptance inside K itself. So here we don't need this L, we can substitute bottoms there. So in this part the argument cannot be used. On the right we have another variant of this tree. We have K with top substituted for the argument. So now this place with the argument can be used, but also the argument has to be accepting, but the argument now is moved here. Okay, so the argument has to be accepting, and this K has to be accepting with this where we can use these places of the argument. Okay, so we have just moved this L out of here to here. Okay, so this is how we change such a term. Now let me show this on an example of a particular grammar, particular recursion scheme. Okay, so we have applied this transformation here to this y, z. Okay, so instead of passing this z to y, we attach it here below this and. Okay, we need two variants of this y. Yeah, like here previously we have two variants of k. Yes, one with bottoms and one with tops. Now somehow this k is y. So for this non-terminal, actually for every non-terminal taking some arguments of order 0, we need two variants. One where we substitute bottom, and the other one where we substitute top. Yeah, in y1 we substitute top for x, and here we substitute bottom. If there are more arguments, we need somehow these two variants for every of the arguments. So at total we need 2 to the power k arguments. Yeah, for every argument we either substitute top or bottom in any combination. Okay, for a more complex example here of order 2, we see that not only non-terminals has to be duplicated, but also all arguments that are of order 1 or higher order. So all arguments that take some arguments of order 0. Yes, we have duplicated them. We have two variants because we substitute. If originally we were just passing y as an argument to z, now we have two variants of y, and we have to pass them as these two arguments. And here we have this kind of application for which we do the transformation. Yeah, we have replaced this y by the two arguments. Okay, so this is essentially how the transformation works. So summing up, we have to create multiple variants of every non-terminal and every argument that takes arguments of order 0, and we pass this bottom or top for these arguments of order 0, and applications of with argument of order 0 are replaced in this way. Okay, and this is easy to generalize. In the paper there is a formal definition of this transformation. There is also a correctness proof, which is just purely syntactical. We just have to show that after such a transformation of grammars, this transformation of grammar results in the transformation of trees presented here. Yes, that this tree is transformed into this tree, and it's easy to see that this new tree is equivalent in the sense of reachability. Okay, the proof was written in Coq. I have given a formal proof in Coq. Yes, so you can be sure that everything is correct, but already while reading this proof in the paper, there is nothing difficult. It's really a simple algorithm and simple correctness proof, much simpler than for the previous algorithms. Okay, so let me summarize. The problem that I have considered is the model checking problem for recursion schemes, that we are given a recursion scheme and an automaton, tree automaton, in our case only reachability automaton. And I have shown a new algorithm solving this problem. So this problem was already solved, as already mentioned, yes, and I have just given a new, simpler solution. Having optimal complexity for future work, I mentioned here two things, just extension of this method to more general problems where we have a parity automaton instead of a reachability automaton, and to a so-called diagonal problem, also called simultaneous unboundedness problem. It's another problem for higher order recursion schemes. Okay, thank you, that's all.